In this exercise, we're going to be introduced to Eulerian graphs named after Euler. Remember him? The bridge man, Hamiltonian paths. Now, Hamilton was a Scottish mathematician who had a different take on the whole business of networks and graphs. So there's your learning intention, and you distinguish and identify those two features of graphs and networks. So we start with Euler. It won't take too long, and then we'll have a look at Hamilton's. Try and remember the difference. Now, I'll give you a heads up now. Euler wanted to connect up, or wanted to cover networks across all the edges, or the paths. Hamilton wanted to go to all the vertices. Now, E for edge, that'll help you remember. Taking that down? E for edges, E for Euler. So Euler helps you find your way around a graph along the edges. Hamilton along visiting all the vertices. Starting with Euler, you've got to remember first of all what a traversable graph is. It's one where you can run your pencil along the graph without lifting it up and cover all the edges. A trail that includes every edge. So repeated edges, you can go to vertices twice. So look at this one on the screen. Can you trace that out? Can you traverse that graph? Yeah? We'll start at A. So we go down there, up to there, down to there. So it's traversable. That makes it traversable. So it's certainly a traversable graph. Now, just to fill in the picture, this one is not traversable. It doesn't. You can't traverse it, and that's because there are 1, 2, 4 nodes. You can't do it. Only talking about traversable graphs in this topic. So, and that's what we've just said, summarizing it. Now, do you remember sometimes you can graph all even vertices, no odds at all? Remember that? Here's one here. There's a 4, 4, and a 4. You should be able to draw that without lifting your pen off the graph. Around here like that, up to there, up to there. But be careful how you do it, mind you. And there we go. So all evens, you can do it. Now, if it's even vertices, you can graph. You take this down and have it in one note. It's all even vertices. It's just a technical term. So this one here, this is an Eulerian graph because they're all even, and that's distinguished from a semi-Eulerian graph, which is 2 odds, like the one below here. 2 odds there, there's a 3 there, and there's a 3 there. So we should be able to start at H and finish. Start at H, finish at F, and that's a semi-Eulerian graph. So if I ask you in a test, is this a semi-Eulerian graph or is it a Hamiltonian circuit or whatever, you will know which is which. It's got to be traversable. If it's traversable and it's got all even vertices, it's an Eulerian graph. If it's got 2 odd vertices, it's a semi-Eulerian graph. And these are used in planning the shortest way around a network. This is an example of an Eulerian, semi-Eulerian graph there, because it had 2 odds, so it's semi. And then that's all to do with edges. If you go to a vertex twice, on this one down here, we went to C twice, we went to C twice here, we went to E twice, B twice. But when we come to Hamilton, we vertices once and once only. First 6 questions of the exercises with Euler. All right, let's move on to Mr. Hamilton. So as I've said, we're going to see vertices. I don't know, it was just a different take as I was explaining just now. if you're delivering to the suburbs of Canberra, you don't want to go from, say, Canberra down to Belconnen and then to Woden and then come back to Belconnen in order to go to Gungahlin. Ideally, you'll go to each suburb once and once only. Here's an example of a Hamilton towns. 1, 2, 3, 4. Don't have to do that. So this is what Hamilton studied, how you can visit all the places on a network and once only, and whether you can or not. Now I've got Hamiltonian paths and cycles. Sometimes, if you're doing deliveries, you actually want to get home again. Now let's look at this one here. We started at A and finished at C, but if you're going to come back home again, you go back through B. Yeah. So that is not a Hamiltonian cycle. Remember, a cycle is where you've got to finish up where you start. So we've done that one different. Instead of going A, B, D, C, is there a different way around that network to go to all the vertices once and once only and finish? So on the board at the moment, in orange, in blue is a path, but if we went A, B, C, A, B, D, C, like that, then it was a cycle. So you would want a more sensible route. And this is an example of a Hamiltonian cycle, starting and ending at A. You can see how they did it. They went down to C, down to F, down to E, D, B, and back to. So if you finish up where you start, it's a cycle. Remember, a cycle is where you finish where you started. So again, something to distinguish. An ordinary graph like this one here, doesn't matter how many times you, it doesn't matter whether you cover all the routes or not, as long as you go to each town once and once only. But that's not finishing up where you start, and that one is. So I think that's size 6F is all about. All questions. And there's your success criteria. So please try and do all the questions in the exercise. Ask, do them if you need help.